Alright, this is day 2 of learning OpenGL. We had installed GLAD and GLFW. Then we also created a window and learned how to change the color of the window. So this is where we are right now. And now we are gonna follow this hello triangle to draw a triangle on the screen. So let me just run this real quick. Yeah, so this is the project right now. Okay, in OpenGL everything is in 3D space, but the screen or window is a 2D array of pixels. So a large part of OpenGL's work is about transforming all 3D coordinates to 2D pixels that fit on your screen. The process of transforming 3D coordinates to 2D pixels is managed by the graphics pipeline of OpenGL. The graphics pipeline can be divided into two large parts. The first transforms your 3D coordinates into 2D coordinates, and the second part transforms the 2D coordinates into actual colored pixels. In this chapter, we'll briefly discuss the graphics pipeline and how we can use it to our advantage to create fancy pixels. The graphics pipeline takes as input a set of 3D coordinates and transforms those to color 2D pixels on your screen. The graphics pipeline can be divided into several steps, where each step requires the output of the previous step as its input. All of these steps are highly specialized. They have one specific function and can easily be executed in parallel. Because of their parallel nature, graphics cards of today have thousands of small processing cores to quickly process your data within the graphics pipeline. The processing cores run small programs on the GPU for each step of the pipeline. These small programs are called shaders. All right. Some of these shaders are configurable by the developer, which allows us to write our own shaders to replace the existing default shader. This gives us much more fine-grained control over specific parts of the pipeline, and because they run on the GPU, they can also save us valuable CPU time. Shaders are written in the OpenGL shading language, GLSL, and we'll delve more into that in the next chapter. Below you'll find an abstract representation of all the stages of the graphics pipeline. Note that the blue section represents sections where we can inject our own shaders. Okay, so yeah, we got vertex shader, shape assembly, geometry shader, tests and blending, fragment shader, and finally rasterization. As you can see, the graphics pipeline contains a large number of sections that each handle one specific part of converting your vertex data to a fully rendered pixel. We will briefly explain each part of the pipeline in a simplified way to give you a good overview of how the pipeline operates. As input to the graphics pipeline, we pass in a list of 3D coordinates that should form a triangle in an array here called vertex data. This data is a collection of vertices. A vertex is a collection of data per 3D coordinates. This vertex's data is represented using vertex attributes that can contain any data we like. But for simplicity's sake, let's assume that each vertex consists of just a 3D position and some color value. All right. In order for OpenGL to know what to make of your collection of coordinates and color values, OpenGL requires you to hint what kind of render types you want to form with the data. Do we want the data rendered as a collection of points, a collection of triangles, or perhaps just one long line? Those hints are called primitives and are given to OpenGL while calling any of the drawing commands. Some of these hints are GL points, GL triangles, and GL line strip. Okay, makes sense. The first part of the pipeline is the vertex shader that takes as input a single vertex. The main purpose of the vertex shader is to transform 3D coordinates into different 3D coordinates. More on that later. And the vertex shader allows us to do some basic processing on the vertex attributes. The primitive assembly stage takes as input all the vertices, or vertex if GL points is chosen, from the vertex shader that form a primitive and assembles all the points in the primitive shape given, in this case a triangle. The output of the primitive assembly stage is passed to the geometry shader. The geometry shader takes as input a collection of vertices that form a primitive and has the ability to generate other shapes by emitting new vertices to form new or other primitives. In this example case, it generates a second triangle out of the given shape. The output of the geometry shader is then passed on to the rasterization stage, where it maps the resulting primitives to the corresponding pixels on the final screen, resulting in fragments for the fragment shader to use. Before the fragment shaders run, clipping is performed. Clipping discards all fragments that are outside your view, increasing performance. A fragment in OpenGL is all the data required for OpenGL to render a single pixel. The main purpose of the fragment shader is to calculate the final color of a pixel, and this is usually the stage where all the advanced OpenGL effects occur. Usually the fragment shader contains data about the 3D scene that it can use to calculate the final pixel color, like light's shadow color of the light and so on. After all the corresponding color values have been determined, the final object will then pass through one more stage that we call the alpha test and blending stage. This stage checks the corresponding depth and stencil value. We'll get to those later of the fragment and use those to check if the resulting fragment is in front or behind other objects and should be discarded accordingly. The stage also checks for alpha values. Alpha values define the opacity of an object and blends the objects accordingly. So even if a pixel output color is calculated in the fragment shader, the final pixel could still be something entirely different when rendering multiple triangles. As you can see, the graphics pipeline is quite a complex whole and contains many configurable parts. However, for almost all the cases, we only have to work with the vertex and fragment shader. The geometry shader is optional and usually left to its default shader. There is also the tessellation stage and transform feedback loop that we haven't depicted here, but that's something for later. In modern OpenGL, we are required to define at least a vertex and fragment shader of our own. There are no default vertex and fragment shader in the GPU. For this reason, it is often quite difficult to start learning modern OpenGL, since a great deal of knowledge is required before being able to render your first triangle. Once you do get to finally render your triangle at the end of this chapter, you will end up knowing a lot more about graphics programming. Okay, so we're gonna have to make our own vertex and fragment shader. Vertex input. To start drawing something, we have to first give OpenGL some input vertex data. OpenGL is a 3D graphics library, so all coordinates that we specify in OpenGL are in 3D XYZ coordinates. OpenGL doesn't simply transform all your 3D coordinates to 2D pixels on your screen. OpenGL only processes 3D coordinates when they're in a specific range between -1 and 1 on all three axes, X, Y, and Z. All coordinates within this so-called normalized device coordinates range will end up visible on your screen, and all coordinates outside this region won't. Because we want to render a triangle, a single triangle, we want to specify a total of 3 vertices with each vertex having a 3D position. We define them in normalized device coordinates, the visible region of OpenGL, in a float array. Alright, so down here, oh wait a second, it should be inside our rendering loop, right? Float vertices, and then these are the 3D coordinates of the vertices of the triangle. Okay, let's define it here. Because OpenGL works in 3D space, we want to render a 2D triangle with each vertex having a Z coordinate of 0. Okay, so it's 0 on Z. This way the depth of the triangle remains the same, making it look like it's 3D. Okay, then it's talking about normalized device coordinates. Yeah, so it starts from -1 and goes up to 1. -1 at the bottom and goes to 1 at the top, so 0 0 is the center of the screen. So it's showing all of these coordinates, or these three vertices of the triangle. With the vertex data defined, we'd like to send it as input to the first process of the graphics pipeline, the vertex shader. Okay, so up here, as you can see, vertex shader is the first part of the pipeline. The main purpose of the vertex shader is to transform 3D coordinates into different 3D coordinates. Okay, I think I already read that. Okay. This is done by creating memory on the GPU where we store the vertex data, configure how OpenGL should interpret the memory, and specify how to send the data to the graphics card. The vertex shader then processes as much vertices as we tell it to from its memory. We manage this memory via a so-called vertex buffer objects, VBO, that can store a large number of vertices in the GPU's memory. The advantage of using those buffer objects is that we can send large batches of data all at once to the graphics card and keep it there if there's enough memory left, without having to send data over one vertex at a time. Sending data to the graphics card from the CPU is relatively slow, so whenever we can, we try to send as much data as possible at once. The data is in the graphics card's memory. The vertex shader has almost instant access to the vertices, making it extremely fast. Excuse me. A vertex buffer object is our first occurrence of an OpenGL object, as we've discussed in the OpenGL chapter. Just like any object in OpenGL, this buffer has a unique ID corresponding to that buffer, so we can generate one with a buffer ID using glgenBuffers function. So we're going to create an object that will hold all the vertex data, and we're going to create a buffer ID for it using the glgenBuffers function. Alright, so we're going to create an unsigned int, call it VBO, and then the glgenBuffers. First argument is 1, and then we pass it the address of VBO. OpenGL has many types of buffer objects, and the buffer type of a vertex buffer object is GLArrayBuffer. OpenGL allows us to bind to several buffers at once as long as they have a different buffer type. We can bind the newly created buffer to the GLArrayBuffer target with the glbindBuffer function. Okay, glbindBuffer, and we are binding to GLArrayBuffer. We are binding our VBO to it. Okay, so here we're not sending it the address, we are just sending the value directly, so it gets this buffer ID. From that point on, any buffer call we make on the GLArrayBuffer target will be used to configure the currently bound buffer, which is VBO. Then we can make a call to the glBuffer data function that copies the previously defined vertex buffer into the buffer's memory. glgenBuffers, glbindBuffers, and then finally glBuffer data. glBuffer data. We tell it to GLArrayBuffer, to work on GLArrayBuffer, and then we pass it the size of our vertices, and then we pass the data itself, the vertices array. finally GL static draw. Okay. GL buffer data is a function specifically targeted to copy user-defined data into the currently bound buffer. Its first argument is the type of the buffer we want to copy data into. The vertex buffer object currently bound to the GL array buffer target. So this VBO will get changed because we bound it to GL array buffer, and then here we pass the GL array buffer target. The second argument specifies the size of the data. Yeah, that's straightforward. In bytes, we want to pass to the buffer a simple size of the vertex data suffices. The third parameter is the actual data we want to send, and then the fourth parameter specifies how we want the graphics card to manage the given data. This can take three forms. GL stream draw, the data is set only once and used by the GPU at most a few times. GL static draw, the data is set only once and used many times. And finally GL dynamic draw, the data is changed a lot and used many times. The position data of the triangle does not change, is used a lot and stays the same for every render call, so its usage type should be GL static draw. If, for instance, one would have a buffer with data that is likely to change frequently, a usage type of GL dynamic draw ensures the graphics card will place the data in memory that allows faster writes. As of now, we store the vertex data within the memory on the graphics card as managed by the vertex buffer object named VBO. Next, we want to create a vertex and fragment shader that actually processes this data. So let's start building those. Vertex shader. The vertex shader is one of the shaders that are programmable by people like us. Modern OpenGL requires that we at least set up a vertex and fragment shader if we want to do some rendering. So we will briefly introduce shaders and configure two very simple shaders for drawing our first triangle. In the next chapter, we'll discuss shaders in more detail. The first thing we need to do is write the vertex shader in the shader language GLSL and then compile the shader so we can use it in our application. Below you'll find the source code for a very basic vertex shader in GLSL. Okay, so this is a vertex shader. First we set the version and core layout, there's something called layout, and then the main function. As you can see, GLSL looks similar to C. Each shader begins with a declaration of its version. Since OpenGL 3.3 and higher had the version number of GLSL match the version of the OpenGL, GLSL 4.20 corresponding to 4.2. Alright. We also explicitly mentioned we're using core profile functionality. Next, we declare all the input vertex attributes in the vertex shader with the in keyword. Okay. Right now we only care about position data, so we only need a single vertex attribute. GLSL has a vector data type that contains 1 to 4 floats based on its postfix digit. Since each vertex has a 3D coordinate, we create a vec3. Okay, creating a vec3 here. Input variable with the name apos. We also specifically set the location of the input variable via layout. Location equals 0, and you'll later see why we're going to need that location. Okay, I think it's telling us about vectors. To set the output of the vertex shader, we have to assign the position data to the predefined GL position variable, which is a vec4 behind the scenes. So here we are setting its value to GL position. So this is like the input to the shader, and then we can do all of our calculations in this main function, and finally we create a vec4 and assign that value to GL position, which will be sort of like the new position of that vertex. To set the output of the vertex shader, we have to assign the position to the predefined GL position variable. At the end of the main function, whatever we set GL position to will be used as the output of the vertex shader. Since our input is a vector of size 3, we have to cast this to a vector of size 4. We can do this by inserting the vec3 value inside the constructor of vec4 and set its W component to 1. We will explain why in a later chapter. The current vertex shader is probably the most simple vertex shader we can imagine, because we did no processing whatsoever on the input data and simply forwarded it to the shader's output. In real applications, the input data is usually not already in normalized device coordinates, so we first had to transform the input data to coordinates that fall within OpenGL's visible region. Okay, compiling a shader, we take the source code for the vertex shader and store it in a const C string at the top of the code file for now. Okay, so it's the same code, but we are storing it in a const character pointer at the top. So here, okay. In order for OpenGL to use the shader, it has to dynamically compile it at runtime from its source. The first thing we need to do is create a shader object, again referenced by an ID. So we store the vertex shader in an unsigned int and create the shader with GL create shader. Okay, so again we're going to create an unsigned int called vertex shader. Let's do that here. And then GL create shader is a function, GL vertex shader, and whatever ID it gives, we're going to store that in our vertex shader variable. We provide the type of shader we want to create as an argument to GL create shader. Since we're creating a vertex shader, we pass in GL vertex shader. Next, we attach the shader source code to the shader object and compile the shader. Okay, so to compile it, we do first GL shader source. Vertex shader, which is, this is our source and this is the ID. Okay, we're passing it the ID, and then the third argument is the address of the vertex shader source, and then the fourth argument is just null. And then finally we tell it to compile the shader. Okay. So this kinda is like, take the source code and put it in this vertex shader, and then we want to compile it. Okay. The GL shader source function takes the shader object to compile to as its first argument. The second argument specifies how many strings we're passing as source code, which is only one. The third parameter is the actual source code of the vertex shader, and we can leave the fourth parameter as null. You probably want to check if compilation was successful after the call GL compile shader, and if not, errors were found. So what errors were found, so you can fix those. Checking for compile time errors is accomplished as follows. Okay, in success, and then we have a log GL get shader IV, pass it the vertex shader, GL compile status, and address of success. What is this GL get shader IV? First, we want to define an integer to indicate success and a store container for error message, if any. Then we check if compilation was successful with get shader IV. For compilation failed, we should retrieve the error message with GL get shader info log and print the error message. So if not success, then we do GL get shader info log, give it the shader 512 null and info log. Okay, so it will store the info log in this string, and then we can just print that out. Okay, I'm gonna separate this. This up here is our vertex shader source, so we already got the variable, and then here we're compiling the shader. And then here we're checking if compilation was successful. All right. If no errors were detected while compiling, the vertex shader is now compiled. Let's actually run this and see if we get anything. Okay, so it didn't print any errors. Let's actually do an else here. Okay, so it says compilation successful. So our vertex shader does indeed compile successfully. Onto the fragment shader. The fragment shader is the second and final shader we're going to create for rendering a triangle. The fragment shader is all about calculating the color output of your pixels. To keep things simple, the fragment shader will always output an orange-ish color. Colors in computer graphics are represented as an array of 4 values. Yep, we can skip that. Okay, so this is our fragment shader. So we have the same version and core profile. Then we have an out vector for called frag color, and then we're setting the frag color to our orange color. So it's kind of different from the fragment shader because we're not doing an out here, we're doing an in, which will be our input position values, and then we're setting that to GL position, which is an internal variable. All right. So I guess we're going to do something similar to this. Fragment shader only requires one output variable, and that is a vector of size 4 that defines the final color output that we should calculate ourselves. We can declare output values with the out keyword that we here promptly named frag color. Next, we simply assign a vec4 to the color output as an orange color with an alpha of 1 being completely opaque. The process of compiling a fragment shader is similar to the vertex shader, although this time we use the GL fragment shader constant as the shader type. Yep, it did create the variable. So we're gonna do fragment shader similar to this. Do it here. Unsigned int fragment shader, and then GL create shader. This returns the ID, and then we tell it that it's a fragment shader, and then we compile it. Let's do that down here. Now this fragment source is not defined, so we're gonna need to copy this and make a fragment shader source up here. I think it should have added that. Fragment shader source. Okay. And then we do a \n end quote. Okay, it's just this. All right, that's it. So that's our fragment shader source code. We're compiling it here. Compile shader. The fragment shader only requires one output variable. Yeah, I already read that. Unsigned int, that's here, and then we compile it. Both the shaders are now compiled, and the only thing left to do is link both shader objects into a shader program that we can use for rendering. Make sure to check the compile errors here as well. Okay, let's check the compile errors here. Success V for vertex shader and success F for fragment shader. Uninitialized, yeah, that's fine. Okay, now it's initialized here. Get shader info. We're gonna pass in the fragment shader here, and then it's just gonna override this info log. That's fine. And then we can say the fragment shader has some error, and then we just print the info log. Cool. Now we need to create a shader program. So for that we do an unsigned int as always. Let's just do that here, I guess. Now let's do it with the shaders. I don't know. Let's put it down here. And then we create the shader program using GL create program. The GL create program function creates a program and returns the ID reference to the newly created program object. Now we need to attach the previously compiled shaders to the program object and then link them with GL link program. So we attach the shaders using GL attach shader. We tell it we want to attach it to the shader program, and we want to attach a vertex shader. Okay, this vertex shader is this ID that we got. Similarly, we attach the fragment shader. If I were just to guess, I would have thought it would be something like this, GL vertex shader in here. But anyway, GL link program, and then we link the program and pass it shader program. The code should be pretty self-explanatory. We attach the shaders to the program and link them via GL link program. Just like shader compilation, we can also check if linking of a shader program failed and retrieve the corresponding log. However, instead of using GL get shader IV, we get GL get shader info log. So we do GL get shader program IV, and then if not success, GL get program info log, and then it's the same. Okay, so I rename the success. Let's do success P for program. If this was successful, if it wasn't successful, we'll get this and put it in the info log, and then we can just print it. So error shader, can do link, I guess. Link failed. Program link failed. All right. Check if linking was successful, and here we are linking the shaders to the shader program. Okay. The result is a program object that we can activate by calling GLUseProgram with the newly created program object as its argument. So this is what we do to activate it. GLUseProgram. Activate the shader program. Let's hope there aren't any errors. Okay, where are we? All right, no errors. Every shader and rendering call of the GLUseProgram will now use this program object and thus the shaders. Oh yeah, and don't forget to delete the shader object once we have linked them into the program object. We no longer need them anymore. Okay, so once they are linked, we can delete them. So we can just do that here. Delete the shader objects, and once they are linked. Right now we send the input vertex data to the GPU and instructed the GPU how it should process the vertex data within a vertex and fragment shader. We're almost there, but not quite. OpenGL does not yet know how it should interpret the vertex data in memory and how it should connect the vertex data to the vertex shader's attributes. Will be nice and tell OpenGL how to do that. Linking the vertex attributes. Okay. The vertex shader allows us to specify any input we want in the form of vertex attributes, and while this allows for greater flexibility, it does mean we have to manually specify what part of our input data goes to which vertex attribute in the vertex shader. This means we want to specify how OpenGL should interpret the vertex data before rendering. Our vertex buffer data is formatted as follows. So we have 3 vertices. Each of those vertices have an x, y, and z coordinate. And then this is bytes, so it's a float. Yeah, it's a float right here. Each one of these is a float, so float takes 4 bytes. So after every 4 byte we have a vertex, and after every 12 bytes we have the data for the next vertex. Okay. The position data is stored as 32-bit 4-byte floating point values. Each position is composed of 3 of those values. There is no space or other values between each set of 3 values. The values are tightly packed in the array. The first value in the data is at the beginning of the buffer. Okay, so we can define all of those, where to start, how big is the data, and what is the offset. So if there was any data in between, we can tell it to skip that. With this knowledge, we can tell OpenGL how it should interpret the vertex data per vertex attribute using GL vertex attribute pointer. Okay, this is actually an important point which I'm pretty sure I'll forget, so I'll put it here. We can tell OpenGL how it should interpret the vertex data per vertex attribute using this function. I don't have to put it here. Okay, so I'm just gonna write it down. That will help me remember it. GL vertex attribute pointer. First argument is 0, which I'm assuming does it say what the first parameter specifies the vertex attribute we want to configure? Remember that we specify the location of the position vertex attribute in the vertex shader. The layout location is 0. Okay, so this is that layout location, I think. And then each position is composed of 3 of those values. So the next parameter is 3. Here we tell the data type. Okay, GL float, GL false. If we want the data to be normalized, if we're inputting integer data type int byte and we set this to GL true, the integer data is normalized to 0 or -1 for signed data and 1 when converted to float. So we are passing float. And then this is some weird math going on here. Size of float, and then we're multiplying it by 3. So I assume this is this one float value, and then each vertex has 3 float values. To define its position, we're gonna multiply it by 3. Okay, and we want to tell it how many bytes it has, so that'll be size of float multiplied by 3. The 5th argument is known as the stride. Yep, this part right here. And tells us the space between consecutive vertex attributes. Since the next set of position data is located exactly 3 times the size of a float away, we specify that using a value as a stride. Note that since we know that the array is tightly packed, there is no space between the next vertex attribute value. We could also specify the stride as 0 and let OpenGL determine the stride. This only works when values are tightly packed. Okay, so in our case 0 would also have worked. Whenever we have more vertex attributes, we have to carefully define the spacing between each vertex attribute, but we'll get to see more examples of that later on. And finally, the last parameter is a void pointer and thus requires that weird cast. This is the offset of where the position data begins in the buffer. Since the position data is at the start of the data array, this value is just 0. We will explore this parameter in more detail later on. Okay, so we are telling it 0, but we have to cast it to a void pointer for some reason. Okay, each vertex attribute takes its data from memory managed by a VBO, and which VBO it takes its data from, you can have multiple VBOs, is determined by the VBO currently bound to GL array buffer. So we have our this VBO object bound to the GL array buffer when calling GL attrib pointer. Since the previously defined VBO is still bound before calling this, vertex attrib 0 is now associated with its vertex data. But since the previously defined VBO is still bound before calling GL vertex attrib pointer, vertex attribute 0 is now associated with its vertex data. Now that we specified how OpenGL should interpret the vertex data, we should also enable the vertex attribute with GL enable vertex attribute array. Giving the vertex attribute location as its argument, vertex attributes are disabled by default. From that point on, we have everything set up. We initialize the vertex data in a buffer using vertex buffer object, set up a vertex and fragment shader, and told OpenGL how to link the vertex data to the vertex shader's vertex attributes. Shader's vertex attributes. Drawing an object in OpenGL would now look something like this. Okay, so that was all just a setup. Where was I? Okay, I've called GL vertex attrib pointer. Now I have to enable the vertex attrib array, pass it to 0. Copy our vertices array in a buffer for OpenGL to use. GL bind buffer, GL array buffer VBO. Okay, is this like everything that we already did? Size of vertices, GL static draw, yep. Then set the vertex attribute pointer. Did that here, and then GL enable vertex attribute array right here. Then finally use our shader program when we want to render an object. GL use program. I call that here. Okay, do that after this. And finally draw the object. Some OpenGL function that draws our triangle. Okay. We have to repeat this process every time we want to draw an object. It may not look like that much, but imagine if we have over 5 vertex attributes and perhaps hundreds of different objects, which is not uncommon. Binding the appropriate buffer object and configuring all vertex attributes for each of those objects quickly becomes a cumbersome process. What if there was some way we could store all these state configurations into an object and simply bind this object to restore its states? Okay, let me read that again. We have to repeat this process every time we want to draw an object. Cool. It may not look like that much, but imagine if we have over 5 vertex attributes, perhaps hundreds of different objects. Binding the appropriate buffer object and configuring all the vertex attributes for each of those objects quickly becomes cumbersome. Okay, so that's why we use a vertex array object, a VOA. VOA can be bound just like a vertex buffer object, and any subsequent vertex attribute calls from that point on will be stored inside the VAO. This has the advantage that when configuring vertex attribute pointers, you only have to make those calls once, and whenever we want to draw the object, we can just bind the corresponding VAO. This makes switching between different vertex data and attribute configurations as easy as binding a different VAO. All the state we just set is stored inside the VAO. Core OpenGL requires that we use a VAO, so it knows what to do with our vertex inputs. If we fail to bind a VAO, OpenGL will most likely refuse to draw anything. Okay, so here it is showing we have a VBO which we created here, this thing. It has all the position data, the stride and all of that, and then we put that in the VBO, and if we have multiple attribute pointers, it will say all of that state. And then we can have a separate VAO for a different VBO, which will store all of this stuff, all of these states. Okay, I guess that makes sense. The process to generate a VAO looks similar to that of a VBO. So we do an unsigned int VAO, and then we do the save GL gen vertex arrays 1 and address of VAO. Okay. To use a VAO, all you have to do is bind the VAO using GL bind vertex array. Wait, what did we use for this? GL bind buffer, and then this is GL bind vertex array. From that point on, we should bind, configure, and the corresponding VBOs and attribute pointers, and then unbind the VAO for later use. As soon as we want to draw an object, we simply bind the VAO with the preferred settings before drawing the object, and that is it. In code, this would look a bit like this. Initialization code done once unless your object frequently changes. We are going to bind the VAO, then copy our vertices array in a buffer for OpenGL to use. Copy our vertices array in a buffer. Okay. Then GL buffer data, similar to this thing, GL buffer data. Size vertices, yeah, it's the same. And then GL vertex attribute pointer, which we already did, and then enable vertex attribute. And then we draw it. We say GL bind vertex array, the VAO, and then this function, and that's it. Everything we did in the last few million pages led up to this moment, a VAO that stores our vertex attribute attribute configuration, and which the VBO is to use. Usually when you have multiple objects you want to draw, you first generate or configure all the VAOs and thus the required VBO and attribute pointers. Store those for later use. The moment we want to draw one of our objects, we take the corresponding VAO, bind it, then draw the object and unbind the VAO again. The triangle we have all been waiting for. Okay, so I have to first set up this VAO. Okay, let's do that. Let's do that here. This is our VAO. I think I can do all of the shader stuff before everything else, because this is gonna be the same regardless. Then after linking, I'll delete shaders, yeah, all of that can come right before we do our VBO VAO stuff here. Okay, this is shader stuff. And this is the end of the shader stuff. And then this is the VBO and the VAO. GL gen vertex arrays. Okay, I'm gonna copy it from here. GL gen vertex GL bind. Let's read through the GL gen vertex arrays. Then we do GL bind vertex array VAO. GL bind buffer VBO. Okay, it's doing it after the VAO. That's fine. We can switch these around. GL buffer data, which is right here, and then set our vertex attributes pointer, GL vertex attribute pointer, which we are doing here. GL enable vertex attribute array, which we're doing here, and then we're calling the use program here. GL bind vertex array VAO. We haven't done that before. Well, GL bind vertex array VAO, GL bind vertex array VAO. Why is it doing that twice? Anyway, trust in the process. Use program, bind vertex array, and then finally some OpenGL function. The triangle we've all been waiting for. To draw our object of choice, OpenGL provides us with the GL draw arrays function that draws primitives using the currently active shader, the previously defined vertex attribute configuration, and with the VBO's vertex data indirectly bound via the VAO. GL use program, we already called that. GL bind vertex array, we already called that. And finally, we call our GL draw arrays. Tell to draw GL triangles. Okay. Takes as its first argument the OpenGL primitive type we would like to draw. Since I said at the start we want to draw a triangle and I don't like lying to you, we pass in GL triangles. The second argument specifies the starting index of the vertex array we'd like to draw. We just leave this at 0. Yep. The last argument specifies how many vertices we want to draw, which is 3. We only render one triangle from our data, which is exactly 3 vertices long. Now try to compile the code and work your way backwards if any errors popped. As soon as your application compiles, you should see the following results. Okay, that's it. No triangle. Okay. Do we have any errors? Nope. Am I supposed to do this inside the render loop? Because it is clearing it right after that, right? It doesn't say where all of this goes. Let me just try to put this after the clearing. And that's our triangle. Great. Now, I don't know if this also needs to be inside the render loop, but since it's working, I'm not going to put it in there. The source code for the complete program can be found here. Let's compare. If your output does not look the same, you probably did something wrong along the way, so check the complete source code and see if you missed anything. Element buffer objects. Okay, so now we have something called the EBO. Do we really need it? We probably do. Okay, so the VAO stores all the attribute pointers, and it also stores the element buffer object, and the EBO stores the index data. All right. First, let's compare it with this. This is our vertex source code, vertex shader and fragment shader source code. This is all the window stuff, and then we're compiling our shaders. Looks the same. Then we're linking our shaders here. Then finally we have our vertices unsigned into VAO and VBO. That's exactly what I did. What's it doing inside? Okay, yeah, so it is calling the use program and the bind vertex array inside of the render loop. So I guess I'm going to do the same. GL bind vertex array is being called here and also here. Seeing as we only have a single VAO, there's no need to bind it every time, but we'll do so to keep things a bit more organized. Okay. So let's call it, it's doing it right before the render loop as well. Okay, yep. Finally, there is one last thing we'd like to discuss when rendering vertices, and that is the element buffer object, abbreviated to EBO. To explain how element buffer objects work, it's best to give an example. Suppose we want to draw a rectangle instead of a triangle. We can draw a rectangle using two triangles. OpenGL mainly works with triangles. This will generate the following set of vertices. As you can see, there is some overlap on the vertices specified. We specify bottom, right, top, and left twice. This is an overhead of 50% since the same rectangle could also be defined with only 4 vertices instead of 6. This will only get worse as soon as we have more complex models that have over thousands of triangles where there will be large chunks that overlap. What would be better solution is to store only the unique vertices and then specify the order in which we want to draw these vertices in. In that case, we would only have to draw 4 vertices for the rectangle and then just specify at which order we'd like to draw them. Wouldn't it be great if OpenGL provides us with a feature like that? Thankfully, the element buffer object works exactly like that. An EBO is a buffer, just like a vertex buffer object, that stores indices that OpenGL uses to decide that what vertices to draw. This so-called index drawing is exactly the solution to our problem. To get started, we first have to specify the unique vertices and the indices to draw them as a rectangle. Okay, so rather than just having vertices and repeating them, what we do is we only store the unique vertices, and then we define our indices. So the first triangle will be drawn with 0, 1 and 3. So this and this vertex, and the second triangle will be drawn with 1, 2 and 3, these three vertices. That's cool. Let's see if we can edit our program. So this is our new vertices array. You can see that when using indices, we only need 4 vertices instead of 6. Next, we need to create the element buffer object, or the EBO, and then we do the same. We call glgen buffers. Let's put it down here. Similar to the VBO, we bind the EBO and copy the indices into the buffer with GL buffer data. Also, just like the VBO, we want to place those calls between a bind and an unbind call. Although this time we specify GL element array buffer as the buffer type. So GL buffer bind, so GL bind buffer. Right here, GL bind buffer. For a VBO, it's a GL array buffer, but for an EBO, it is a GL element array buffer. And then we put the data in there. Like so, GL buffer data, GL element array buffer, and we pass the size of indices, we give it the data, and it will also be a GL static. Note that we're giving GL element array buffer as the buffer target. The last thing left to do is to place the GL draw arrays call with GL draw elements. GL draw elements, where's the GL draw elements? GL draw arrays. Okay, I think we have to replace this. Okay, note that we're now giving GL element array buffer as the buffer target. The last thing I have to do is to replace the GL draw arrays, this function, with the GL draw elements function to indicate we want to render the triangles from an index buffer. When using GL draw elements, we are going to draw using indices provided in the element buffer object currently bound. So GL bind buffer, GL element array buffer, EBO. So like that. Wait a second, are we already doing that? Anyway, GL draw elements, GL draw arrays, GL draw elements, GL triangles. I think this is how many indices does your EBO have. So in our case we have 6 indices. GL unsigned int, I guess that's the data type. Yep. And finally 0, I guess, is the starting point. Yep, it's an offset. The GL draw elements function takes its indices from the EBO currently bound to the GL elements array buffer target. This means we have to bind the corresponding EBO each time we want to render an object with indices, which again is a bit cumbersome. It just so happens that a vertex array object is also keeps track of element buffer objects. The last element buffer object that gets bound while a VBO is bound is stored as the VBO's element buffer object. Binding to a VAO then also automatically binds an EBO. Okay, so the last element buffer object that gets bound while a VAO is bound is stored as the VAO's element buffer object. binding to a VAO then also automatically binds the EBO. Okay, so you don't have to bind the EBO separately. You bind the VAO, it also binds the EBO. The VAO stores the GL bind buffer calls when the target is GL element array buffer. This also means it stores its unbind calls, so make sure you don't unbind the element array buffer before unbinding the VAO. Otherwise, it doesn't have an EBO configured. The resulting initialization and drawing code now looks something like this. Bind vertex array object GL bind vertex array VAO, which is right here. GL bind vertex array, where is it? Yep, GL bind vertex array. Okay, so this is for generating, and then we are binding here. GL bind buffer, the VBO right here. GL buffer data. Okay, so it's doing that before binding the VBO. GL bind buffer EBO. Okay, it's doing that afterwards. And then finally, it also does the GL buffer data for the EBO. And then finally, we bind the VBO. GL vertex attribute pointer. Okay, it's not doing that here because it's also doing that down here. Maybe that's the VBO. Okay, let's go. Let's comment this for now. Drawing code in the render loop is GL use program. We're doing that right here. Then we are doing a vertex array EAO. Cool. And then we're doing GL draw elements triangle right here. Then GL bind vertex array. Okay, it's not doing the EBO in here anymore. And then I think it's unbinding. GL bind vertex array. Zero. Running the program should give you an image as depicted below. The left image should look familiar, and the left image is the right image is the rectangle drawn in wireframe mode. Wireframe rectangle shows that the triangle indeed consists of two triangles. Nope, we have an error. Frame not in module. Don't think I can understand any of this. Okay, so what am I doing wrong? Oops, okay. So first we're doing the GL bind vertex array. GL bind vertex array VAO. Copy our vertices array in a vertex buffer for OpenGL to use. GL bind buffer GL array buffer VBO. So okay, I think this is not supposed to be here. Okay, this needs to go up. GL bind data, this thing. Yep, I think this should work now. Okay, and that's our rectangle. Cool. To draw your triangles in wireframe mode, you can configure how OpenGL draws its primitives via GL polygon mode, GL front and back, GL line. The first argument says we want to apply it to the front and back of all the triangles, and the second line tells us to draw them as lines. Any subsequent drawing calls will render the triangle in wireframe mode until we set it back to its default using GL polygon mode, GL front and back, GL fill. Okay, let's try that. So before drawing here, let's set it as or maybe we only need to do this once. Okay, yep, it draws it as a wireframe. Let's try to do this before running our render loop. Okay, yeah, so you only need to do that once, and then any draw calls that it does, it's gonna draw it as lines. That's a handy little function. Draw as lines, and the opposite of that would be GL fill. Okay, if you have any errors, work your way backwards. We didn't have any errors. If you managed to draw a triangle or a rectangle just like we did, then congratulations, you managed to make it past one of the hardest parts of modern OpenGL. No kidding, drawing your first triangle, that is a difficult part since there is a large chunk of knowledge required before being able to draw your first triangle. Thankfully, we now made it past that barrier, and the upcoming chapters will hopefully be much easier to understand. So I guess that's it. We have made our rectangle, the fruits of our labor. Okay. So in the next chapter, I guess I'll do this next week. We're gonna learn some GLSL.